Hello friends, in our earlier discussion we talked about the basic combinational logic circuits like the half and full adders, subtractors and the use of adder circuit as subtractor. In today's lecture we shall be talking about parallel binary adders, their IC datasheet characteristics and their application. We shall also be discussing the ripple carry and the look ahead carry adders. Parallel binary adders. Two or more full adders are connected to form parallel binary adders. In this section, we will talk about the basic operation of this type of adder and its associated input and output functions. As you saw earlier and illustrated here, a single full adder is capable of adding two 1-bit numbers and an input carry. To add binary numbers with more than 1 bit, you must use additional full adders. When one binary number is added to another, each column generates a sum bit and a 1 or 0 carry bit to the next column to the left with 2-bit numbers. To add two binary numbers, a full adder is required for each bit in the number. So, for 2-bit number, 2 adders are needed, and for 4-bit number, 4 adders are used, and so on. The carry output of each adder is connected to the carry input of the next higher order adder as shown in figure for a 2-bit adder. Notice that either a half adder can be used for the least significant position or the carry input of a full adder can be made 0 or grounded because there is no carry input to the least significant bit position. The least significant bit of the two numbers are represented by A1 and B1. The next higher order bits are represented by A2 and B2. The three sum bits are sigma 1, sigma 2 and sigma 3. Notice that the output carry from the leftmost full adder becomes the most significant bit in the sum, that is sigma 3. 4-bit parallel adders. A group of 4 bits is called a nibble. A basic 4-bit parallel adder is implemented with 4 full adder stages as shown in figure. Again, the LSBs, that is A1 and B1 in each number being added, go in the rightmost full adder. The higher order bits are applied as shown to the successively higher order adders, with the MSB, that is A4 and B4 in each number being applied to the leftmost full adder. The carry output of each adder is connected to the carry input of the next higher order adders as indicated. These are called internal carries. In keeping with most manufacturers' data sheets, the input labeled C is the input carry to the least significant bit adder. C4 in the case of 4 bits is the output carry of the most significant bit adder, and sigma 1 through sigma 4 are the sum outputs. The logic symbol for 4-bit parallel adder is shown in figure. In terms of method used to handle carries in a parallel adder, there are two types: the ripple carry adder and the carry look ahead adder. These are discussed later in this lecture. truth table for a 4-bit parallel adder. Table shows the truth table for a 4-bit adder. On some data sheets, truth tables may be called function tables or functional truth tables. The subscription n represents the adder bits and can be 1, 2, 3 or 4 for a 4-bit adder. C n minus 1 is the carry from the previous adder. Carries C1, C2 and C3 are generated internally. For example, here we will find out the sum and output carry for the addition of following two 4-bit numbers 1100 and 1100. Looking at the numbers, we see that for n equal to 1, A1 is equal to 0, B1 is equal to 0 and C n minus 1 is equal to 0 from the first row of the table. Here sigma 1 is equal to 0 and C1 is equal to 0. For n is equal to 2, A2 is equal to 0, B2 is equal to 0 and C n minus 1 is also equal to 0 from the first row of the table. Here sigma 1 is again 0 and C2 is 0. For n equal to 3, A3 equal to 1, B3 is equal to 1 and C n minus 1 is again 0 from the fourth row of the table, and sigma 1 is again 0 and C3 is equal to 1. For n is equal to 4, A4 is equal to 1, B4 is equal to 1 and C n minus 1 is equal to 1 from the last row of the table, and sigma 1 is equal to 1 and C4 is equal to 1. So C4 becomes the output carry and the sum of two numbers 1100 and 1100 is 11000. An example of a 4-bit parallel adder that is available in IC form is the 74LS283. For the 74LS283, VCC is pin 16 and ground is pin 8, which is the standard configuration. Recall that logic gates have one specified propagation delay time TP from an input to the output. For IC logic, there may be several different specifications for TP. The 4-bit parallel adder has the 4 TP specifications as shown in figure, which is part of a 74LS283 data sheet. Adder expansion. The 4-bit parallel adder can be expanded to handle the addition of two 8-bit numbers by using two 4-bit adders. The carry input of the low order adder C0 is connected to ground because there is no carry into the least significant bit position, and the carry output of the low order adder is connected to the carry input of the high order adder as shown. This process is known as cascading. Notice that in this case the output carry is designated C8 because it is generated from the 8th bit position. The lower order adder is the one that adds the lower or less significant 4 bits in the number, and the high order adder is the one that adds the higher or more significant 4 bits in the 8-bit numbers. Similarly, 4 4-bit adders can be cascaded to handle two 16-bit numbers. Application. An example of full adder and parallel adder application is a simple voting system that can be used to simultaneously provide the number of yes votes and the number of no votes. This type of system can be used where a group of people are assembled and there is a need for immediately determining opinions. In its simplest form, the system includes a switch for yes or no selection at each position in the assembly and a digital display for the number of yes votes and one for the number of no votes. The basic system shown in figure is for a 6-position setup, but it can be expanded to any number of positions with additional 6-position modules and additional parallel adders and display circuits. Here each full adder can produce the sum of up to 3 votes. The sum and output carry of each full adder then goes to the two lower order inputs of a parallel binary adder. The two higher order inputs of the parallel adder are connected to ground. Because there is never a case where the binary input exceeds 0011 or decimal 3. For this basic 6-position system, the outputs of the parallel adder go to a BCD to 7-segment decoder that drives the 7-segment display. As mentioned, additional circuits must be included when the system is expanded. The resistors from the input of each full adder to ground assure that each input is low when the switch is in the neutral position. When a switch is moved to the yes or the no position, a high level is applied to the associated full adder input. Ripple carry versus look ahead carry adders. As mentioned in the last section, parallel adders can be placed into two categories based on the way in which internal carries are handled. Those categories are ripple carry and look ahead carry. Externally, both types of adders are the same in terms of inputs and outputs. The difference is the speed at which they can add numbers. The look ahead carry adder is much faster than the ripple carry adder. A ripple carry adder is one in which the carry output of each full adder is connected to the carry input of the next higher order stage. The sum and the output carry of any stage cannot be produced until the input carry occurs. This causes a time delay in the addition process as illustrated in figure. The carry propagation delay for each full adder is the time from the application of the input carry until the output carry occurs. Assuming that the A and B inputs are already present, full adder 1 cannot produce a potential output carry until an input carry is applied. Full adder 2 cannot produce a potential output carry until full adder 1 produces an output carry. Full adder 3 cannot produce a potential output carry until an output carry is produced by FA1 followed by an output carry from FA2 and so on. As you can see in figure, the input carry to the least significant stage has to ripple through all the adders before a final sum is produced. The cumulative delay through all the adder stages is a worst case addition time. The total delay can vary depending on the carry bit produced by each full adder. If two numbers are added such that no carries occur between stages, the addition time is simply the propagation time through a single full adder from the application of the data bits on the inputs to the occurrence of a sum output. The look ahead carry adder. The speed with which an addition can be performed is limited by the time required for the carries to propagate or ripple through all the stages of a parallel adder. One method of speeding up the addition process by eliminating this ripple carry delay is called look ahead carry addition. The look ahead carry adder anticipates the output carry of each stage and based on the inputs produces the output carry by either carry generation or carry propagation. As illustrated in the figure, carry generation occurs when an output carry is produced or generated internally by the full adder. A carry is generated only when both input bits are ones. The generated carry Cg is expressed as the AND function of the two input bits A and B given by the equation Cg is equal to A dot B. Carry propagation occurs when the input carry is rippled to become the output carry. An input carry may be propagated by the full adder when either or both of the input bits are ones. The propagated carry Cp is expressed as the OR function of the input bits given by the equation Cp is equal to A plus B. The three arrowheads symbolize ripple propagation. The output carry of a full adder can be expressed in terms of both the generated carry Cg and the propagated carry Cp. We get an output carry of 1 if it is generated by the full adder or if the adder propagates the input carry and Cin is equal to 1. This relationship is expressed as Cout is equal to Cg plus Cp into Cin. So friends, this brings us to the end of our discussion in this lecture and therefore we sum up. We learnt how to use full adders to implement a parallel binary adder, talked about the addition process in a parallel binary adder and discussed with example the use of the truth table for a 4-bit parallel adder. Then we discussed the difference between a ripple carry adder and a look ahead carry adder and talked about the advantages of look ahead carry addition and finally defined carry generation and carry propagation. So that is it for today. See you in the next lecture with more on combinational logic circuits. Thank you very much.